Hello everyone, we are Group 37 and today we are presenting the research paper Action Scene Graphs for Long Form Understanding of Egocentric Videos. We have divided the paper into 6 parts. Each of my teammates will be explaining one part. I am Bukesh Yadav. I will be walking you through introduction and related work section later on. Let's start by understanding the problem authors are trying to solve. Uh, what are egocentric videos? Imagine someone wearing a GoPro or smart glasses that record what they are doing. Maybe they're cooking or doing some other task. This kind of video where camera shows what the person is seeing is called egocentric video. Now, egocentric videos are usually long. They can go on for minutes or even hours. So to understand these videos, we need to look at not just one action, but a series of actions. So we can get a big picture of what's going on, like like picking up a knife with right hand and cutting vegetable. This is a series of actions. So what's the problem? Most current techniques only understand short clips, maybe a few seconds long. They just label actions like cut apple, cut vegetable. They don't understand how the actions connect over time. They miss the bigger story. This makes it hard to build systems that can maybe predict the next action or summarize what have been done till now in the video. What can be a possible solution? This paper introduces something new called EASG, egocentric action scene graphs. Think of it like it's a graph. It's just a simple graph made up of nodes and connections. A node can represent a person or a object like spoon or an action like cut. The connection shows how things are related. For example, person picks knife and cuts vegetable. And now what's the cool part? The cool part is these graphs change over time, like frame by frame. Each frame will create a new graph. So they show how actions unfold, not just a single moment. And why do we need these? Before understanding why do we need these, let's dive deep in how are authors trying to use these graphs. The authors use a popular data set called Ego4D, and they manually added these detailed graphs to it. They also built a baseline model that tries to predict these graphs automatically from video, and they tested how well these graphs work in 2 tasks. So we can say that the two tasks were predicting what will happen next, like an action anticipation, and summarizing the whole video, that is activity summarization. I've explained why this paper was written, the introduction part. Up next, my teammate will explain how these egocentric action scene graphs are actually built and used. Thanks for listening, and I hope this gave a good foundation to understand the rest of the paper.
Thanks, Bhupesh, for setting the stage and helping us understand why egocentric video is so important for action understanding. Just to quickly recap, egocentric videos are those recorded from first person point of view. That means the camera is placed in on the person's head or chest, and we see the world as they see it, including their hands, the object they touch, and the space around them. So, for example, if someone is making a sandwich, the video will show their hand picking up bread, using a knife, opening a jar, all from their perspective. Now, this viewpoint gives us a rich stream of visual information, but it also comes with challenges. The camera is always moving, hands may block objects, and action can be fast and subtle. So, simply labeling actions as take bread or spread butter isn't enough. We need a way to describe not just the action itself, but also how things are connected, how they changes over time, who is interacting with what, and that brings to us to the key idea of, in this paper, egocentric action scene graphs or ESGs. Let's talk about why we need a new representation. Traditionally, action recognition in videos uses what's called verb-noun pair. These are basic label like open door, cut apple, or pour water. And while that works okay for short, simple actions, it really struggles with more complex scenes. Imagine you are watching someone cook a meal. There are multiple actions happening at once. The person is holding a spoon, stirring soup, reaching for salt, or maybe even checking a timer. Verb noun labels don't capture how these actions are related. They also don't show what happened before and after each action. So the author of this paper proposed something more powerful, a graph structure that can represent all the elements in the scene, including the camera, wearer, objects, and the relationship between them. This structure is called egocentric action scene graph. Now let's look more closely at what an ESG actually is. At its core, an ESG is a type of graph similar to a network or a diagram made up of two parts, nodes, which represent key things in the scene, like the camera wearer, objects such as cup or kettle, and action like pour or cut, and edges, which show how those nodes are connected. For example, hand pours water into cup or knife cuts apple. So instead of just saying cut apple, the graph gave us a structural picture. It shows that the camera wearer hand is holding a knife, the knife is interacting with the apple, and that the result is a sliced object. This is a big step forward because it tells us not just what action is happening, but how multiple elements are involved and how they are connected. And unlike traditional scene graphs used in images, these ESGs are built specifically for egocentric video. That means they are designed to track the perspective of the camera wearer, the person doing the task, and their direct interaction with object in a time-aware way. One of the most unique and important features of ESGs is that they capture the flow of time. Every action in a video unfolds over a short period. It doesn't happen in just one frame. To represent these each ESG is divided into three temporal stages. Pre. This is the stage before the action begins. For example, when someone picks up a kettle and stands near a cup. PNR. This stands for peak narrative frame. It's the moment where the action is most like clearly happening. In this case, the kettle is tilted and water is pouring into the cup. Post. This is the result after the action has finished. The cup is full, the kettle is back on the table, and the hand might be moving away. These three snapshots, pre, PNR, post, are used to build different versions of scene graph across time. The objects are often the same, but their relationship and position changes. This gave us dynamic view of how the scene evolved, which is something you can't get from a single static level. So now that we understand how ESGs work, let's talk about why they are useful. Because ESGs give us a detailed structured view of object and their interaction over time, they open the door to more advanced tasks like action anticipation, predicting what the person might do next based on how the objects are arranged and what action has already taken place. Activity summarization, turning long videos into compact, meaningful summaries that explain the sequence of event. And even robotics, where a robot can learn how to do tasks by watching a person perform it, using the graph structure to understand the order and relationship of actions. So ESGs aren't just about labeling videos, they are about helping machines actually understanding human behavior and reasoning in complex real world tasks. And with that, I will hand over to Asif, who will explain how these ESGs are created, annotated, and structured in the dataset. Thank you.
Hello everyone, this is Asif, and I'm gonna continue what after Tarun basically explained EASG, and I'm gonna explain Ego 4D dataset. The Ego 4D dataset samples a subset of 221 Ego 4D clips run from 181 unique videos, each originally labeled for the state change object detection, which is SCOT. And these annotations that we make give us per action 3 salient frames: the precondition, point of no return, and the post condition frames. We'll see what they mean exactly in a moment, and how they anchor each action scene graph temporally. Each clip CI contains a sequence of these tuples, uh, AIT1, AIT2, like these, and each tuple AI is basically a combination of pre-PNR and post-tuple, post frames, and then this bundle each of these will have 6 components. The X denotes pre-PNR or post in AIXT. It will contain F as the frame index and as noun class of the manipulated object, uh, B naught as the bounding box of that object. BLH and BRH are the bounding boxes of the left and right hand, the visible left and right hand. It will be phi if they are not visible, and R is the free-form narration text. Now, the pre-PNR and post are basically frames, and they define our core terminology. Okay, precondition frame is basically the moment just before the action starts when the objects are untouched. PNR is the point of no return, the critical frame where the action becomes irreversible. The take has begun. It basically describes whatever the action has been taken completely. And the post condition frame is the moment after the action completes, showing the result. It explains us what is the outcome of the thing just happened. These three, when kept together, they define the temporal anchor for each action. Grounding our graph in concrete video frames. By grounding, I mean associating each object node with its bounding boxes in the pre-PNR and post frames, ensuring every graph node has concrete visual reference. Then we make a direct object and an indirect object. A direct object is between a verb and a normal noun, and an indirect is between noun and noun. So direct object is an object that's object node that's connected to the verb node via a direct object edge, indicating that it's being manipulated. And an indirect object connects only via the prepositional edges, example like with and from, showing contextual relationships. Then we start our annotation process. This was definitions. So in annotation, what we do is that we first initialize. We add a camera viewer node, VCWT, and a verb node, vverb, with and we create an edge, VCW to vverb, and we name it action. This is a special edge that's basically supposed to denote that the camera viewer takes action. Then we extract the verb from the narration text R and then create an object node NKT for the manipulated noun with its pre-PNR post boxes B naught. Then we link vverb to the verb vertex to NK via direct object edge, as we said earlier. This was our initialization, and after we complete our initialization, we go for refinement. For refinement, we take 3 Amazon mturk workers, and using those workers, we will create 3 final graphs. Now, workers view the 5-second clips around PNR plus pre-PNR post frames. Then they verify or correct the verb noun pairs, rarely about like 5, rarely like less than 5% required change. Then add indirect objects, example right hand or table, and choose the linking prepositions like with, from, etc. Then draw bounding boxes on pre-PNR post for each new object. Then we get our final result, which are the 3 candidate graphs, G1, G2, G3 per timestamp. Now this is to capture the diverse perspectives and catch errors early on during pre-processing only. Now, this just this is a direct annotation pipeline that they used in the paper. We start, then as I said, we view the current verb noun pair, inspect PRE, PNR post frames, and inspect the clip sample. We check is our verb noun pair incorrect or not. If it's correct, if it's incorrect, then we provide a new verb noun pair because that's required, of course, and then we mark it for review. If it's not, then we check if there are if it's correct, then we check if there are other objects to add. If there are no other objects to add, then we add. Then we check if there are any other indirect objects other than hands, and if not, we end it. And if there are other indirect objects other than hand, then we annotate those objects with on boxes, and then we mark it for review. Now, if there were no other objects to add, if there were objects to add, then we select the role and the indirect object, and we add that object, and we like repeat our pipeline from the no part as shown. Then we go to validation, the second stage of our filter system. What we do is we aggregate the three annotations and resolve conflicts in a single validation pass. Verb noun agreement, verb noun disagreement or agreement, whatever, they select the correct pair. Edge ambiguity picks the right preposition. Hand use checks left, right, or both hands use. Spatial relations demands yes or no checks directly. This was an example right in the paper, and this is for graph validation. Now the procedure is clearly shown in the left side, and these are the example questions that are asked by the annotator, the refiners. Like for example, if we have an error in filtering verb noun pairs, like if the three annotators differ on the core verb noun pair, we ask, does the camera wearer take bowl or press do? The answer is take bowl as shown in the image. Then for edge disambiguation, we check like if multiple relations exist. The camera viewer takes bowl with left hand or camera viewer takes bowl on left hand. We select the one which is semantically correct. Then we do the hand identification. If annotators disagree which hand, we directly ask which hand does camera viewer take bowl with right hand, left hand, or both. Then we get our answer accordingly. Then we check for indirect object links as spatial relationships. Like, is the bowl with floor? Yes or no? And we get our answer as shown. Using these targeted questions, a single validator reconciles all discrepancies and produces a final graph G. That's it from my part. Now, temporal recollection will be explained by Yashvi.
Hi everyone, in this part of the presentation, I will be talking about two important components of our paper, temporal recollection and the dataset statistics and comparisons for the newly proposed EGO 4D EASG dataset. Let's begin with temporal recollection. Initially, the skin graphs we build called GI of T are static. That means even though a video spans many frames, the graph at each time step is constructed individually. This introduces a problem. The same object can have different node IDs at different times. Take a simple example. Imagine you are watching someone cooking and a plate is present in the scene across multiple frames. In the static graphs, the plate might be labeled as n1 of t at one frame and then n2 of t plus 5 and so on, even though it's clearly the same plate. So there's no temporal reconsistency in object identity. This is where temporal recollection comes in. This process looks at the entire sequence, let's say all graphs from t equal to 1 to t, and globally reassesses the object nodes. In it matches objects across time and reassigns node indices so that each physical object retains a consistent ID. So now the plate is always n1 of t and n1 of t plus 1, so on. So no matter the timestamp, this gives us a dynamic, temporally coherent scene graph, which is critical when analyzing actions or reasoning about object usage over time. By doing this, we can now track how objects are manipulated or moved, even across longer activities like assembling a product or preparing a meal, something not possible with traditional static graphs. With this, let us now look at the dataset and how it compares to others in the field. The Ego 4D EASG dataset is an extension of the Ego 4D dataset and is specifically designed for long-term egocentric video understanding. Here are some key stats. It includes 221 annotated video sequences, 11.4 hours of video. Average labeled segment is about 3.1 minutes long, which is quite long compared to other datasets. Each video has around 28 annotated scene graphs, one for each salient action. The annotation includes 407 unique object classes, 219 verb classes, and 16 relational classes. Now what's important is every object in these graphs is grounded in video with bounding boxes in three keyframes, pre, PNR, and post. That's over 30,000 bounding boxes in the training set alone and another 19,000 in validation. These groundings make the graphs more symbolic and visually tied to real video content. Now let's compare this with other video scene graph datasets. Most existing datasets like VID, VRD, VID-OR, Action Genome, and even Home Action Genome are either short form or non-egocentric. They usually cover clips that are only a few seconds long and focus on static and semi-dynamic scenes. In contrast, R1 is fully dynamic, meaning object relationships change over time and are tracked. It is also egocentric, which gives a unique perspective where the camera is worn by a person, so the view constantly changes with their motion. It is the only dataset that includes very verb nodes in the graphs, explicitly representing actions as standalone nodes, not just as relationships. This is major difference. In most scene graphs, an action like open door or would just be a relationship like person opens door. But in EASG, open is itself a node. This gives us much more flexibility in analyzing or generating long form actions. Also the average graph count per video is much higher, 28.3, which reflects finer granularity of annotations. In short, R1 is first to combine egocentric perspective, temporal dynamic graphs, and action-centered reasoning in long-form videos. It sets a new benchmark for egocentric video understanding. To wrap up, both temporal recollection and the rich large-scale annotations in the Ego 4D EASG dataset enables a much deeper and time-aware understanding of human activities from a first-person view. This makes dataset incredibly valuable for tasks like anticipation, activity summarization, and many other long-form video applications.
So
So now that we understand how temporal recollection is used to maintain object consistency across these networks, frames, and my friends have explained the data set part, let we move on to how these ECG graphs are actually generated. So from now I will be explaining you the generation part, the baseline model architecture and its performance. So let me first explain the generation part, my first slide. So the generation part is basically divided into three tasks. The first task is called the edge collection or the HCLS. So basically here the objective is to identify the relationship between objects. It is a quite straightforward task. The model just looks at a pair of objects and just determine the relationship between them. So basically, let's say we divide the video into frames, and in each frame, in let's say in one frame, we have something. The camera shows that there is a wearer holding a ball. So the model simply took these two pairs, wearer and ball, and makes a relationship between them that hand holds ball like something. So the first part is simply straightforward. Now the second part is called a scene graph classification or SGCLS. The task is more comprehensive. It doesn't just identify relationship. It basically classify how object and actions are involved in this relationship. So basically, uh, remember the example which I just told you. Instead of just hands hold ball something, the model classify hands as a manipulator and ball as an object. So if there is a similar action in any other frame, we will be able to capture it. Uh, Finally, the third task is called the EASG classification. It is the complex among these three. The model here must not detect and classify the object or your action. It also learn to link them together to form the complete time evolving scene graph. So basically, the frames and the actions will changes over time. So this in this part, the model learn to classify actions on the basis of these time frames. So basically these three tasks from the core of ESG, they form the basic object relationship to complex action graphs. Now the second slide, here I will be explaining the baseline model architecture. So, so what the author propose is as follows. Basically, the input to the model consists of three key video frames. Basically they called them pre, PNR, and post. These frames represent different points in the action sequence. Like let's say in a frame there is action going on, so there is something called before the action, second something during the action, and after the action to capture that action completely. And these three corresponding to pre, PNR, and post. For instance, let's say in a sequence where the camera wearer takes a cup and place it on a table, then pre would show the cup in the hand. PNR will show the cup being placed, and the post will show the cup resting on the table. Like basically the action before, the action after, and the action actually. So once these frames are fed in the model, the first step is feature execution. Basically, it is done using a pre-trained model. The author use a pre-trained model like slow fast. They extract visual features from each frame to form the initial input representation. Now, after that, it enters the processing stage. Here, the model consists of three task-specific layers, as I have shown in this slide. One for HCLS, one for SGCLS, and third for EHGCLS, which I just explained in the previous slide. Uh, the output of them is a structured representation that include predicted verbs, object, and their relationship. As I have explained, the first it classifies the object, then action, and then time depending relationship between them. So basically, after classifying these three things, it forms a complete scene graph for each frame. And the overall architecture is just effective as starting point. So basically, this baseline model they have used. So the output is basically the action verb as I have written. Now on the third slide, I will be explaining the baseline model performance. Uh, so how the model actually perform these tasks. I have explained you how they are using this baseline model. Now I will explain you the performance. The author evaluated this model using something called recall K. Uh, what it is, it measures how accurately the model predict relationship between objects and actions. So what it does is as follows. In the first task, the edge CLS as I explained you, there are three tasks: SCLS, SGCLS, and the third one. So the first task, SCLS, the model achieve a relative high scores. This is expected because identify simple object relationship is simply trivial. It is simply easy. Like you are simply detecting objects no, which will be using as nodes. Now the second task which we use is they use is SGCLS. Here the model performance starting to dip. Now the model has to classify both objects and the actions while maintaining the connection between them. For instance, as I take the example of like the hand holds cup, but also hand places cup on the table. This added complexity, and as a result, the score get reduced. And the third one, which is the most complex task, which is called the ESG as I explained. Here, the model needs to form a complete scene graph that capture the entire action. Also, it involves time dependency, and output should be in a structured format. Since this involves predicting multiple nodes edges simultaneously, so this basically reduces the score a drop further. So overall, the baseline model performs well in simpler tasks, but struggle with more complex ESG tasks where you have to define multiple relationship between multiple similar objects over the time and over frame. So it highlights the need for more sophisticated method. Basically, we need to fully capture the dynamics. So basically, this is the performance analysis of their baseline model, and this concludes this my part, which includes this generation part and the baseline model selection and their performance. Now Manjeet will walk us through these generated graphs and how they are applied to downstream tasks like action, anticipation, and the summarization. Then we will conclude the paper. Thank you.
Hello. So continuing from the previous explanation on how graphs are generated from video frames, I'll now walk you through what we can actually do with those graphs. In other words, the downstream tasks. These tasks are what we test whether ESGs are truly useful for understanding egocentric or first-person videos. Let's get started. What are downstream tasks and why are they important? Once we have ESGs which capture detailed action object relationships over time, the next step is to use them to perform meaningful tasks like predicting future actions, generating video summaries, assisting behavior modeling, robotics, and more. In this paper, the author focused on two specific downstream tasks: action anticipation and long form activity summarization. What makes their approach elegant is they don't build any new neural network. Instead, they simply feed structured ESG based prompt into GPT-3. Okay, let's dive into each task in detail, starting with action anticipation. So, what is this task all about? Imagine you are watching a video recorded from someone's points of view, like a GoPro mounted on their head. You see that at time T1, the person grabs a slice of bread. At T2, they open a jar of peanut butter. Now, can you guess what they'll do next? Most humans can maybe spread peanut butter on bread. This is exactly what the model is asked to do in action anticipation. In this task, we are given a sequence of past action. These graphs are linearized. They are turned into a simple sentence text like text prompt and then passed into GPT. Here's an example. Hand grabs bread at T2, hand opens peanut butter jar, and at T3. The GPT sees this and predicts the next line. For example, hand spreads peanut butter on bread. On your on your slide, you'll see this shown as timeline where the input action from a prompt and GPT completes it. Now let's look at the maths behind it. So this is a formula that the model is considering while predicting the predicted verb and pronoun. So here we bar explain predicted verb and bar explain refers to predicted noun, and G1 and D2 are the previous graph that we are giving to our GPT. Basically, here it is using the conditional probability method to guess the best suited pair of V and N. So the key points here are that there is no training of fine tuning. As I have already told that we are using pre-built GPT-3 models, and tasks are controlled by prompt only. And the evaluation here is done by top 1 and top 5 accuracy, which is a very much normal and very much in use in these tasks. So our second task is summarization, long form activity summarization. While the first task focuses on predicting the next steps, this one focuses on the big picture. What if we want a short human readable summary of a long video? Let's say you have a 3-minute video of someone preparing breakfast. You don't want to describe every small action, just a meaningful overview like the person retrieved milk from the fridge and prepared breakfast. This task is called long form activity summarization. How does it work? We take all ESGs from the full video, say T1 to T20, and convert them into a text shape like this. At T1, hand open fridge. At T2, hand grab milk. At T3, hand pour milk into bowl. And at T20, hand places bowl on table. Then at the end of the prompt, we simply write summary. Now GPT-3 is asked to summarize the entire sequence in 1 second. On your slide, you will see how this process is visualized. The input is a block of linearized action description, and the output is a single meaningful summary sentence. Mathematically, this is so. Let us dive into the mathematical modeling of the. So mathematical formulation is shown on your slide. That is S bar equal to R max of probability S given all the previous graphs, where S bar is the predicted summary sentence and G1 to GT are the ESGs or the graphs from the entire video. What makes this powerful is that GPT understands how to shift from sequence completion to summarization based on just one word in the prompt summary. This task is extremely useful in scenarios like automatically generating video captions, creating step-by-step guides, content indexing, or storyboarding for long egocentric video. So, while understanding the performance, for task 1 we have used top 1 and top 5 accuracy, but in task 2, the summarization, the generated summaries are compared to the human written one using 3 standard NLP metrics. That is BLAU, that checks how many words in the sequence match. Sorry. ROGUL focuses on longest common matching phrases, CRDR, that measures how informative and relevant the summary is. Key line to remember is that higher the value for value, ROGUL and CDR indicate better summarization quality, meaning the generated summary is more similar to what a human would write. So I would wrap up from here. Thank you.
Since now you have a good level of understanding of this research paper, now let's talk about what research already exists and how this paper builds on it. In the past few years, researchers started using graphs to better understand images and videos. But why are they focusing on graphs? Because graphs are good at capturing relationship. Like if a person holds spoon, then relationship between person and spoon is very clear. Some works use graphs to detect objects or answer questions about the scenes. Other papers use graphs for videos, especially to track objects and actions over time. But here's the thing, most of them work on third-person videos like YouTube videos or surveillance footage. They don't focus on egocentric videos where the camera is worn by a person. Now, a few papers have tried using graphs in egocentric settings, but not too many. Some looked at combining audio and video, some used graphs to help with navigation, but none of them focused on understanding long-term actions like this paper does. This is the first time someone has built a full evolving action graph for egocentric videos with proper objects, verbs, and relationships. There are many datasets with graph style labels like visual genome for images and action genome for short videos, but none of them are designed for egocentric long form understanding. That's why this paper extends Ego 4D dataset and creates a new dataset called Ego 4D EASG. So in short, related work shows graphs are useful, egocentric vision is challenging, and this paper is the first to combine both in long form and structured way. Thank you. That's all from our side. I hope we were able to provide a good level of understanding of this research paper to you.